Hi, and welcome back to part 2 of Combinational Logic, part 2 lecture. In this part, we're going to talk about the design procedure. And first of all, we need a general statement about combinational circuits. So although we've looked at them a lot before, we can just say that a combinational circuit has a set of m Boolean inputs, a set of n switching functions, each mapping the 2 to the m input combinations to an output, such that the current output depends only on the current input values. And this is an important characteristic of combinational logic circuits, and you will see once we get to the next lecture when we talk about sequential logic circuits how that differs, because we actually store the system state as well. So here's the block diagram of it showing the inputs, combinational logic circuit, and the outputs. The design procedure requires that we get a specification where we would write a specification for the circuit if it's not already given. Then we do a formulation step where we derive a truth table and the initial Boolean equations that define the relationships between the inputs and the outputs. This may also be given in the specification. The next step is the optimization approach, where we apply two-level and multi-level optimizations, and then we draw a logic diagram that includes the ANDs, ORs, and inverters. The fourth step is the technology mapping step, where we map the logic diagrams to the implementation. And then finally a verification step, where we verify that our final design matches the initial specification. And we can do this either manually or using a simulation. It's important to remember that order: specification, formulation, optimization, technology, and verification, or special friend on TV. In order to demonstrate this process, we're going to go through a design example. The first step being the specification, where we require a BCD to XS3 code converter. This converter is going to transform the BCD code into an XS3 code for the decimal digits. So we have the BCD code words for the digits 0 through to 9, which are the 4-bit patterns 0000 to 1001. And then remembering from the first lecture where we have the XS3 code, which is simply the BCD code with the addition of 0011, as in adding 3 to all of the BCD code words. And we require an implementation that is a multi-level circuit and also a NAND gate implementation. So we write out the formulation of this by putting the truth table down, and this formulates how we would turn the input variables A, B, C, D, which are the BCD codes on the left-hand side of this table, to the output variables W, X, Y, and Z on the right-hand side. Also important is to mention where the don't cares are. So the don't cares are obviously for values of 10 to 15. Any value down here are all don't cares from 1010 to 1111. We're going to do the two-level optimization using the Carnot maps. So I've put the truth table down here so that's easy to reference, and then we're going to be determining the min terms for the outputs. So for W is true from 5 through to 9, the index 5 through to 9. And then remembering that it's don't care for any values from 10 through to 15 here. And that's the same for the other outputs as well. For X is true for indexes 1, 2, 3, 4, and 9. 1, 2, 3, 4, and 9. Y is true for values 0, 3, 4, 7, 8. And Z is true for index values 0, 2, 4, 6, 8. So we'll check those. So that's correct. That's correct. Correct. And correct. All right, now we have to draw some rectangles around these. So we can find an 8, a 4, and another 4. So W equals A or BD or BC. 4 here. And the 2 there. So notice for X, Y, and Z, we have these don't cares that are not being covered, and that's fine as long as we're covering the min terms where there's a value of 1. That's the result for W, that's the result for X, which we got, the result for Y, which we got, and the result for Z, which we got. And when we write the equations out, that's correct. In this step of the optimization, we're going to take the equations that we got from the Carnot map for W, X, Y, and Z, and we're going to optimize them slightly further. So if we were to count the gate count, and remember this gate count does not include the negations, So we would count 7 for this first one. We've got 1, 2, 3, 4, 5, 6, 7. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gates for this one. This is 1, 2, 3, 4, 5, 6. And this one, since it's only at one negation, there's no gates, then it's 0, giving a total of 23. However, we can notice that there is a CD that happens many times in there. So let's say this is also equal to A plus B outside of C or D. And this is equal to not B outside of C or D plus B, C, D. So if we were to take out the C or D as a factor and call it T1, like in this way, then we can slightly simplify down to W, X, Y, and Z. Now we need to count the T1 as part of the gate count. So we've added another 2 to the gate count here, but then we've reduced this one down to 1, 2, 3, 4. Where it was previously 7, and we've reduced this one down to 1, 2, 3, 4, 5, 6, 7, where it was previously 10, and these two stay the same. So now our total G is equal to 19 rather than 23. And that circuit looks like this, given the inputs of A, B, C, D, the outputs of W, X, Y, and Z, and the inclusion of this T1 being C or D, and that output is used for both W and also X. Here is what we've got so far, with G equaling to 19 and the inclusion of T1. And we can also realize that not T1 is equal to not C or D, which is equal to not C and not D. And then we can use that additional factor there to get rid of the not C, not D here, and the not C, not D here, and replace it with the complement of T1 in this way. And then we've reduced it even further from 19 all the way down to 16. And that's what this circuit looks like. So you can see before where we had the T1, which is C or D, we didn't actually have it going into this NOT gate. We just had it going to the W and X outputs via other combinational logic. But now we've used the fact that the complement of T1 can also be used to reduce the circuit further. And then we use that negated T1 for another input to X and another input for the Y circuit. The fourth step of the design process is the technology mapping, and we want to map to a library that contains inverters and 2-input NAND gates. And since only NAND gates are available in this case, and we know that a NAND gate with a single input is the same as an inverter, then we can map it straight to 2-input NAND gates only. In order to map to the 2-input NAND gates, we have to assume that the gate loading and the delay is ignored, and we will look at that more in later lectures. We have to assume also that the cell library contains an inverter and an n-input NAND gate where n is equal to 2, and we also need the AND or inverter schematics for the circuits. The mapping is accomplished by replacing all the ANDs and the ORs with the NAND gate and the inverter equivalent circuits, and then cancelling the inverter pairs. This means obviously if you have a NOT and another NOT, it's just the same as one wire, and we'll look more at replacing the AND and OR symbols with the NAND gates in the next slide. So given this AND symbol where we have a number of inputs all being ANDed together, we can replace that with the same NAND gate with the bubble on the end and then an inverter. And where we have an OR gate, we can do inversion before coming into the NAND gate. So we will repeat the following pair of actions until there's at most one inverter between a circuit input and a driving NAND gate output and the attached NAND gate inputs. So as I said before, 2 inverters in a row is the same as a wire. One inverter with multiple splits should be changed so that we have the inverters after the splits. So here's an initial circuit with AND gates, OR gates, and NOT gates. Where there was the AND gate at the top, we've replaced this with a NAND and a NOT, and the same for these other AND gates. For the OR gates, we've replaced it with inverters going into a NAND gate, and then we can realize that, for example, 5 and 6, these inverters will cancel each other out, as will 1 and 2, as will 3 and 4. And so once we've replaced those, we end up with all NAND gates and inverters, and that completes the technology mapping step if we were to map to NAND gates. If we had to map to NOR gates, we have to assume once again that the gate loading and delays are ignored. We have to assume also that the cell library contains an inverter and n input NOR gates with 2 or 3 or more gates, as well as the AND or inverter schematics for the circuits being available. In a similar way to the NAND gate, the mapping is accomplished by replacing AND and OR symbols with the NOR gate and the inverter equivalent circuits, and then cancelling the inverter pairs. So we would replace an AND with inverters going into a NOR gate, and we would replace the OR with a NOR gate which is inverted afterwards. And then as we did with the NAND gates, we repeat the following pair of actions until there's at most one inverter between a circuit input or driving NOR gate output and the attached NOR gates inputs. So 2 inverters in a row becomes a wire. If you've got the output of one inverter being split up, then we push the inverters towards the outputs of the next gates, and that way it's easier to cancel out groups of inverters. So here's the NOR mapping example. We've got the same circuit that we had for the NAND mapping example. We replace this AND gate with 2 inverters going into a NOR gate, and we do the same for these other 2 AND gates. For the OR gate at the end, we replace that with a NOR gate and then an inverter afterwards. And then you can see that we can cancel out, for example, the inverter 1 and 2 gets removed, and so there's a direct connection between the output E and the input to this NOR gate. We can remove the 1 and 3 inverters so that the output of E also can go directly to the input of this NOR gate. D also, instead of D going through an inverter and then another inverter prior to going into the NOR gate, it's just a wire, and that's all the optimization we can do for that particular circuit. Go back to our design example and the technology mapping from this logic diagram, and then removing all the ANDs, ORs, and replacing them with NANDs, with 2 input NANDs, will look like this. I think it's probably a good idea if you look at the 2 circuits next to each other and then trace your way through there so you can convince yourself that the technology mapping is actually correct. The next stage of our design procedure is the verification stage, where we show the final circuit design implementation and the original specification. And if we've had to do steps in formulation in order to create truth tables and Boolean equations, and that they're not in the original specification, then we have to be very, very sure that the formulation process is flawless for the verification to be valid. We're trying to verify the original specification, and so if we've taken steps between specification and formulation that may have introduced errors, then we don't want to be verifying our potentially incorrect formulation. We want to compare the final circuit truth table with the specified truth table. There's 2 main ways of verifying, one being the manual logic analysis, which is fine if the circuit is quite simple. We would find the truth table or the Boolean equations for the final circuit that we've created, and then we want to compare the final circuit truth table with the specified truth table. Using a computer, we could simulate the final circuit and the specified truth table using different test inputs and make sure that they match what we expect. And obviously, we don't have to include don't cares. It's only testing the combinational circuit for applications of possible care input combinations. That is, in our case, from BCD to XS3, it's from 0 to 9, and they're the ones that we actually care about getting a correct output for. So I'm not going to go through every single one of these, but I suggest if it was something simple like this, that it's worthwhile doing that yourself as an exercise. I'll pick out a few to trace through. So let's do this first one with our equations. We have W equaling A or B and T. A and B, C and D are all 0. Then clearly W is going to be 0 as well. X, not B, and T. So since C and D are both 0, then not B and T or B and not T, both going to be 0. CD or not C or D, that is the negation of that. So since C or D is 0, then the negation of that gives 1, and Z equaling to not D. So since we have 0 here, not D is 1. So it's quite a time-consuming process if you were to go through for every single one of the inputs and check each of the outputs, but it's an important process that you do to make sure that the tables match. Let's do another one, but we'll use the circuit that we've created. So given A is 0, then we have 1 here, B is 1, so we have 0 here, C is 1, so we have 0 here, D is 1, so we have 0 here. So T gives 1 here, means that we have 1 here, we have 1 here, have 0 here, have 0 here. This gives 0, this gives 1, this gives 1, this gives 1, this gives 0, gives 1, this gives 0. So then the output should be 1, 0, 1, 0. So that's correct for that circuit, and for that set of inputs, we're getting the correct output. Clearly, this would be easier to do in simulation, where we can feed this list of inputs and check the outputs much more quickly than we could on paper. But I wanted to give you the idea about how to follow that through a circuit and follow that through the equations. Now we're going to show what it would look like if we were doing it in simulation. We use the schematic editor in the program like Xilinx, or perhaps a text editor to enter the gate level representation of the final circuit. And then we use the waveform editor to enter a test consisting of a sequence of inputs. And that sequence of inputs would perhaps be from 0 to 9 BCD inputs. So this test should guarantee the correctness of the circuit if the simulated responses are to be correct. And we've got to make sure we test all the possible care input combinations, because otherwise it's difficult for us to verify the output for sure. So here is the circuit that we came up with, and we would put this schematic into the circuit in Xilinx, and we'll look at that more in the tutorials. And then we would enter a waveform, and this waveform ABCD should be values from 0 to 9, and you should verify this. So first of all, we see that D is going 1 and 0, 1 and 0, C. And so at this point, we have 1. At this point, we have 2. At this point, we have 3. At this point, we have 4. Here we have 0, 1, 0, 1, which is 5. Here we have 0, 1, 1, 0, 6, 0, 1, 1, 1, 7, 1, 0, 0, 0, 8, 1, 0, 0, 1, 9. And then afterwards, these all go to 0 again. So it counts from 0 all the way through to 9 and then starts at 0 again. Here we have the input waveform, which was on the previous slide, and then we're looking at what the W, X, Y, and Z output values are to make sure that we're actually getting an XS3. So it starts off 0, the output being 3, then this is 4, 1, 0, 0. So this is 3, 4, this one's 5, 0, 1, 0, 1. This is 6, 0, 1, 1, 0. This is 7, 0, 1, 1, 1. This is 8, 1, 0, 0, 0. This is 9, 1, 0, 0, 1. 10, 1, 0, 1, 0. 11, and then finally 12, and then back to 3 again. So that's what we would expect. We go between 0 and 9, and then back to 0. Here we go between 3 and 12, and then back to 3 again. So yes, the simulation output combinations match the original truth table. After those previous examples, you've probably started to realize that the circuits can become quite complex when we're mapping the inputs to the outputs. Clearly then, it's advantageous for us to decompose those functions into smaller pieces, which we're going to call blocks. And this is really how hierarchical design starts. We're trying to decompose each of the blocks' functions into smaller and smaller blocks. And we just repeat that until all of the blocks are what we would consider small enough to manage, small enough to understand. Any block that's not decomposed is called a primitive block, and the collection of all the blocks, including those decomposed ones, is the hierarchy. Also, so we don't have to double work, wherever possible we're trying to reuse function blocks. If we create the function blocks to be general enough and modular enough that we can put them into different types of designs, then this can often make our life much easier and make the design process much quicker. It also allows us to create complex designs out of these simple reusable component blocks. As a general rule, you've got to make sure that those blocks are verified, well understood, and that it's well documented so that future you feels very proud of present you for making the block so easy to understand and also able to be remembered because of the documentation. And then you would put them in libraries for future use. And this, of course, is a good engineering principle to have. In terms of the design procedure, the two most common ways to think about it is top-down design and bottom-up design. Now, in this subject, we're going to be focusing on top-down design. And top-down design starts from the abstract, the high level. a specification and becomes increasingly detailed as we decompose and successively refine our design. Whilst the bottom-up design starts with very detailed primitive blocks and combines them into larger and more complex functional blocks. In general, the design process that we would advocate would usually proceed from top down to the known building blocks, ranging from complete CPUs all the way down to primitive logic gates or electronic components. And that's the end of part 2, so I'll see you in part 3. We're going to start talking about functional blocks.